So as Pablo foreshadowed, topological phases can change your life. And now we have Dr. Zhen Bi to talk about the universe in topological phases. While he's connecting, I'll just mention that I've followed this field of double beta decay closely for 35 years. And I'll summarize the situation by we're getting there. This is a great problem. So.
Thanks, Peter, for the nice introduction. And my name is Zhen Bi. I'm a condensed matter theorist. And today I'm going to tell you something about topological phases and topological phase transitions. So before I talk about what's topological phase, let's go back a little bit to talk about the philosophy of condensed matter physics. So I always got these questions from friends, families, sometimes strangers like Uber drivers. What is condensed matter physics? So I think it is very nice summarized by these two quotes. One from ancient Chinese philosopher Lao Tzu. He told us the Tao produced one, one produced two, two produced three, three produced all things. The other one is from Phil Anderson, a Nobel laureate who actually came up with the name condensed matter physics. His famous quote is more is different. So in a weak sense, condensed matter physics is just about to understand what happens when you put many particles, many atoms or molecules together. So what is the, although each individual particles, we may know how they move and interact with each other, their collective behaviors may be much more complicated and much more beautiful. If we look around our world, we'll see many beautiful phases of matter. The most familiar ones are made out of water molecules. They are solid ice and also water liquid. Although they made out of the same molecule, the ice has a solid shape. It's very rigid, but the water has no shape. There are other interesting phases of matter. For example, there are material which can generate a magnetic field around it. We call them magnetic material. And there are more interesting phases of matter when you cool it down enough. You will find that it can conduct electricity for no cost. Those are superconductors, which we use it in the magnetic levitation trains. So we are surrounded by those interesting phases of matter. And as a condensed matter physicist, we want to understand why they behave this way. But being more realistic, we don't usually work with pretty pictures. We work with the so-called phase diagram. So on the left panel, it is a phase diagram of water. The axes are temperature and pressure. The phase diagram simply tells you under certain condition what phase this material will be in. Okay, on the right-hand side, it is the phase diagram of a magnetic material. At a very low temperature, this material will exhibit magnetic property and generate a magnetic field around it. And as we heat up this material, at certain temperature, the material loses magnetic properties. They become totally non-magnetic. So the pressing question for us, for the theorists, is what is the true distinction between these phases? Let us look at the magnetic material more closely. And the answer can be answered if we zoom in the material and look at the macroscopic properties. So if we look at the magnetic side, all the individual magnetic moment associated with each electron, they are roughly aligned to each other if you look closely into this material. And this is an ordered state, what we call an ordered state. And if you look at the non-magnetic side, the individual magnetic moment associated with electrons, they are randomly pointing to all the directions. So this is a disordered side. On the most theoretical footing, what's the true difference between these two states are the symmetry properties. A symmetry of the system is some operation that you can do on the system which keep the system invariant. So for example, we can do an operation that's reversing all the moments in the system. In the ordered state, we'll clearly see that after this reversing operation, the north pole will become south pole of the magnet. So clearly, this operation changed the state. But on the right-hand side, in the disordered side, if we reverse all the moments, we'll find roughly the system is also disordered. The global property of the system never change. So we see the ordered state actually break this reversing symmetry, and the disordered state preserve this symmetry. So that's the true difference between the two states, and it's responsible for all the interesting behaviors they have. So with this picture in mind, we can also understand how the phase transition happened. At very low temperature, the individual momentum of the electrons want to align with each other to lower the energy. As we heat up the material, each individual atoms gets more kinetic energy, and the spin of the electron can move around, and the total magnetic moment of the system actually drops as we raise the temperature. And at some critical temperature, the kinetic energy actually dominates the system, and the total magnetic moment drops to 0 at the phase transition. And after the phase transition, the material becomes non-magnetic. Okay, so based on the symmetry principle, we can actually come up with a schematic classification of the phases of matter. We can actually understand many of the phases of matter around us. So take a material, there's usually a very symmetric phase. And if we tune some parameter in the system can break some symmetry and enter different ordered states. Okay, and we also understand the phase transition between the ordered state and the symmetric state, just like the picture we showed before. This paradigm was led by Russian physicist Landau in the 1920s and 30s, and it has been a very successful way to understand phases and phase transitions for more than 100 years. But really, as a condensed matter theorist, as a theorist, we love to unify all the things in a universal framework, but we're also driven by curiosity. We want to ask the question, whether our framework is complete. Is the symmetry principle the whole story for classifying or understanding phases of matter around us? So that's really the topic I'm going to talk about today. And nature always has a way to surprise us. In 1980s, people find this integer quantum Hall effects. So integer quantum Hall effects essentially is study a cloud of electrons confined in a two-dimensional world. And if you add a very big magnetic field at very low temperature, the properties of the system is very amazing. What people can measure is the electrical conductance as a function of magnetic field. And what you will find is that the electrical conductance form this stair shape. And each step or plateau has a very extremely precise quantized electrical conductance. It is equal to an integer times some fundamental constant. And even more remarkable is that this quantization plateau, this electrical conductance plateau are very robust. No matter how dirty your sample is, you always get the same plateaus. Okay. And later on, it will, so each of the plateaus are actually new phases of matter. Each of the plateaus are different, but they are not different by their symmetry properties. So there must be something else that differentiates these states. Later on, people realized that this is related to the topology of the ground state wave function of these many electron states. So in some abstract sense, you can imagine the electron wave function has some shape. And each of the steps correspond to, so the electrical conductance actually correspond to the number of holes in the ground state wave function. For example, for the first plateau, they correspond to 0 hole in the wave function. The next one corresponds to 1 hole, and so on and so forth. So the number of holes actually is a topological invariant for a manifold. So that the topological invariant meaning that this property won't change if you do smooth deformation on the system. Therefore, this quantization plateau is so robust. But that's too abstract. Let me give you a simple picture that hopefully tells you what is really going on in the system. So we all know that electrons, under a very, very, very big magnetic field, they form circular orbits like this. So in the bulk of the system, the electrons want to form circular orbits. Therefore, they are localized there. They cannot conduct electricity. But if we look at the edge of the system, what we find is that because the electron cannot go out of the sample, it can form this skipping orbit, which runs along the edge of the sample. Okay, these edge modes are actually responsible for those quantized electrical conductance. And if we look at those edge states, they are actually very special because they only move along one direction. And we call those chiral edge modes. Those chiral edge modes are very robust because when an electron meets a disorder or impurity on the edge, has no choice but go around the impurity and move along again. So this conducting edge mode is very robust against any kind of perturbation. And if we look at different plateaus, in the bulk of the sample, they are actually the same. They are all localized electron orbits, but different plateaus actually correspond to different numbers of chiral edge modes on the boundary. And the number of chiral edge modes is actually equal to the topological index of the system. Okay. So if we consider, when we consider the marriage between symmetry and topology, many new phases of matter can emerge. And one class of them is the so-called symmetry-protected topological phase. And it was pioneered by our Professor Xiaogang Wen at MIT. And Pablo mentioned this two-dimensional topological insulator to you in the introduction. And hopefully I'll give you a simple enough picture to understand what's going on in the topological insulator. So we know that the electron has spins. It can either be spin up or spin down. Let's suppose that we engineer the topology for the spin-up electron to form a quantum Hall state as we just introduced. And we form a reversed quantum Hall state for the downspin electron. So right now, the system has an insulating bulk, but has two edge modes. But the edge modes are not chiral because we have a left-moving channel and we have a right-moving channel. The left-moving channel carries spin up. The right-moving channel carries spin down. Okay? Because they are not chiral, they are not stable, because this forward-moving electron can meet some disorder and be scattered back and move backwards. So these edge states are not stable, and they cannot conduct electricity. But suppose in the system we have some symmetry. Suppose we have a spin conservation symmetry. That means the spin of the system cannot change. Then the scattering process we just described cannot happen, because that process we described flip the spin of the electron. Therefore, combine the topology and the symmetry of the system, we get stable edge state which can conduct electricity. So topology and spin together give us a non-trivial, new phases of matter has non-trivial edge states. And as Pablo mentioned, this was the material was first proposed by theory group at MIT in 2014, and they realized this state just last year, and I think they have the best sample to realize this state in the world. Okay, so the concept of symmetry-protected topological phase can actually be generalized to many different systems. They can have different symmetries and different dimensions. For example, the topological insulator we mentioned can have a 1D version, 2D version, and 3D version. And there can also be topological superconductor, topological magnetism. And the topological property not only exists in electronic system, it can also exist in bosonic system. There is a large set of research activity focusing on the symmetry-protected topological phase, trying to understand their properties and classify all of them. And some of my PhD work was focusing on that. And we proposed one of the first experimental realization of a bosonic analog of the topological insulator in 2 dimensions. And what we propose is a two-dimensional system consists of a bilayer graphene. And the phenomenology of the state is that it is insulating in the bulk. On the edge, there are symmetry and topology-enabled edge state. But the peculiar thing about the edge state is that the electrons don't want to propagate along the edge singly. So the electron on the edge actually want to grab a partner in the other layer and propagate together. So the propagating mode on the edge actually has bosonic statistics. So this is a bosonic analog of the topological insulator we mentioned before. So in the later part of the talk, I'm going to tell you something new I'm working on at MIT. It's also related to topological phases of matter. But let's take a step back to look at the big pictures. So with this topological principle, new topological principle, we not only have symmetry breaking phases, we also have new states matter, which are distinguished by topologies. Okay? So then there's a pressing question. There's a new question for us theorists that how do we understand the phase transitions between different topological phases? Let me give you some motivation to tell you why this is the interesting and the hard problem. First of all, we cannot use the old picture for phase transitions for the symmetry breaking case. Because as we mentioned in the earlier different, for example, in the quantum Hall case, different quantum Hall plateaus, they are not differed by their bulk properties. If you look at the bulk of the system, they're all the same. They have no symmetry distinctions. Their distinction comes about when you have a boundary of the system. Okay? So the symmetry breaking picture doesn't work in this kind of phase transition. Another thing is that the topology is a discrete concept. You know, we always talk like chocolate ball has a 0 hole, and the donut has 1 hole in it, and so on and so forth. We never have an object that has half a hole in it. So that means, in other words, topology cannot change continuously. This tells us that topological phase there must be something interesting happen at the topological phase transition. And the topological phase transition demands a new framework to describe them. And I want to tell you, I'm going to, hopefully I can convince you that the topological phase transition actually happens in a very exciting way. It usually involves broken electrons and emergent gauge fields. So let me first introduce these two concepts, broken electrons and emergent gauge fields. So how do we actually split electron? And you may have the following image of a crazy scientist who is trying really hard to chop an electron into 2 halves. It is very reasonable you think this guy is crazy because we know the electron is an elementary particle. It's indivisible. It has been proven numerously by experiment. But the idea that we can have elementary excitation in the system actually behave like a fraction of electron in the system is actually not crazy. And this has already been realized experimentally, and the system is called fractional quantum Hall states. So the fractional quantum Hall states has the same setup as the integral quantum Hall states. You put electron in a 2-dimensional world, and you add in very strong magnetic field at very low temperature. Because the electrons strongly interact with each other, the collective motion of electron actually behaves like a third of the electron. Or in other words, the quasi-particle excitation of the system actually behaves like a third of electron. So those are called Lofgren quasi-particles. And in general, they are called anyons. Anyons are very interesting because they carry fractional charge, and even more interesting, carry fractional statistics. So those are really very bizarre particles. And they have many potential applications in future quantum information technologies. So it's not very crazy for us to think the electron can be broken into pieces. And gauge fields are also not very distant concept. A gauge field actually exists everywhere in our universe. So gauge fields are invented to describe interactions between subatomic particles. If we look at the atom, inside the atom there are electrons and nuclei. Electron and nuclei, they interact with each other through the electromagnetic force, which is a form of so-called abelian gauge field. If we look closely into the nuclei, we will find that protons and neutrons. Protons and neutrons, they interact with each other through, and also interact with the electron through the electric weak force. And those is an example of the so-called non-abelian gauge field. And if we look closely into a proton, there are 3 quarks, and the quarks interact with each other through another non-abelian gauge field, which mediates a strong force. Okay, so the non-abelian gauge fields are really the glues for the elementary particle. They glue the elementary particles together to form the nuclei and form the atoms. So sometimes they are also called gluons. So now let me tell you what actually happens at the topological phase transition after we introduce these 2 key concepts. So what we find in our theories is this. Let's suppose we start from some non-topological state, some non-topological superconductor, which naively you can think as a chocolate ball. And then we tune some parameter in the system can go through a phase transition from a non-topological state to a topological state, which is denoted by the donut. So in the non-topological state, electrons behave like an ordinary particle. But when the system hits a phase transition, the electrons are completely broken into pieces, and we call those pieces e-quarks. You can either think them as electron quarks or emergent quarks. And those, together with the e-quarks, there are also an emergent non-abelian gauge field, which mediate interactions between them. So at the critical point, the electrons are completely broken. And after we tune through the phase transition, the emergent gauge fields disappear, and the electron quarks that combine together again become the normal electron. So pictorially, this theory tells us, well, how do we actually transform a ball to a donut? We can actually go through a stage where we melt the chocolate totally into a soup and then rebuild it into a donut. So that's actually what happens at the topological phase transition. So let me briefly summarize what is new and interesting for this topological phase transition. Near the topological phase transition, as we said, the electrons are completely broken into pieces. They are electron quarks. And the emergent gauge fields appear at the critical point to mediate interactions between them. And this is very similar to the picture of quarks and gluon in particle physics at high energy. So if you have a piece of topological material and you tune some external parameter in the system, at some special point in the system, you will find an emergent universe that consists of electron quarks and emergent gluons. And after you tune through the phase transition, the universe just disappears. So let me acknowledge my collaborators, my PhD collaborators, Yizhuang Yu and Sen Kexu at UCSB. And I also want to thank my collaborators at MIT, Sento and Max, who is collaborating on the topological phase transition. And let me finish by thanking Neil and Jane for the great support. Without you, none of this will happen. And I will leave you with this phase diagram and also an old saying in ancient Chinese. It is called 麻雀虽巧，五脏俱全. The translation is small but complete. I think it fits very well to our story that even something small as a rock, if you look closely, you will find a wonderful new universe emerge in it. Thank you very much.
I'll call on Neil or Howard to start.
I'll start with, I thought the electron was a point particle with no particular dimensions.
Yes.
I thought the electron was a point particle with no particular dimensions.
Yes.
In an earlier diagram, you give its dimensions right there, 10 to the minus, right there at the top. And then you go ahead and infer that you could break it down into e-quarks.
Yes.
Is that a totally theoretical concept?
Okay, so the electrons here are actually elementary particles, but the broken electrons here, as we call the e-quarks, they're actually collective motion of it. So each of the e-quarks, they're actually very large size. It's just collective behavior of electrons. They collectively behave like a fraction of the electrons. So those are called quasi-particles. They are not real fundamental particles. But if you just look at the low energy of the system, pretend you don't know what is fundamental, what is not, then they are as good as fundamental particles.
I have the same question actually I asked last time. This is all theory.
Yes.
Any hope of building an experiment to actually show this?
So to be honest, right now we don't know to tune which parameter we can go through this particular phase transition. But in principle, this phase transition can happen. Yeah, I have no further words on that.
Okay, thanks.
Any questions from the audience? Julieta?
This E-quark field, does it look exactly like the strong force? Is it always a third of the electron charge? It doesn't have kind of color symmetry? Like,
Yeah, so in this particular story, the gauge, in a more technical word, the gauge field between them is SU2 gauge field. So the three quarks actually carry vector representation under that SU2 gauge group. It's slightly different from the standard model SU2, because the standard model SU2, the matters carry fundamental representation, but here they carry a vector representation.
If I read this plot correctly,
Yes.
If I went to 0, right, where you get the breaking, and then I
Yes.
went up in temperature,
Yes,
I would have a room temperature something,
yes.
right? So first question is, how far up does that hold, and what would that something be?
Okay. So at the critical point, there's no energy scale. So if you go up in temperature, then this the properties of this fan is controlled by the critical point. So in this fan, you actually see many electron, quarks, and gluon pop up in this system. And there's always the upper cutoff for our story. And the upper cutoff is actually the interaction strings. So in the system, for our story to work, there's always a UV cutoff. And if the temperature go beyond the UV cutoff, you see different physics.
Okay, let's thank Zhen Bi again.